Welcome to this TI Australia webinar for Specialist Mathematics. Insight session, we're looking at applications of differential equations, and in particular looking at inflow-outflow mixing problems. I'll be your host, James Mott. So Insight's webinar, we'll be looking at constructing DEs that describes inflow-outflow problems. We'll be unpacking worded problems and trying to organise the information in an efficient way. We're using our old friend DSolve to solve some differential equations on the CAS. We'll be trying to calculate some quantities of interest, such as concentration, the amount of outflow of a problem. And we'll be looking at some exam-style questions throughout tonight's webinar and seeing how we can use CAS in an efficient way to tackle them. So the setup here is that we've got some sort of tank with a liquid in it, and we have a liquid that's flowing into the tank that may contain some sort of chemical or solution. Now, in the tank initially, there might be some sort of chemical in there that'll be often specified in the question. And for simplicity, we're going to assume that the liquid in the tank is stirred continuously and uniformly so that the chemical inside there is nice and uniform. And as some liquid is flowing in, some liquid is also flowing out, and often it's flowing out at a known rate. So what we like to sort of understand in this sort of scenario is to figure out how much chemical we have in the container at any time. And the way we can think about this is if we know the amount that's flowing in and the amount that's flowing out, we can construct a differential equation, and then from the differential equation, we can work towards determining how much of the chemical is actually in there. So the underlying principle of this differential equation to determine the rate of change of the amount of chemical in the container is to consider the rate at which the chemical is flowing in minus the rate at which the chemical is flowing out. So there we're looking at the difference between the inflow and the outflow. So when it comes to trying to unpack a worded question, often we're presented with a slab of information, and we like to sort of represent this in a nice diagram or table. Now, in your classes, you may have your own way of doing things, and your teachers might have your own way of doing things. So I will say that this is simply one way of representing this information. If you've got a way that works best for you, then go for it, but here's just an alternative way. So when we're tackling a question, what we like to identify is any sort of inflow or outflow quantities, the initial mass, volume, concentration that we have, so they're often given in the question. And then throughout the process of tackling these problems, we're going to see how the volume changes and the concentration changes over time. So it's best to, when tackling these questions, get a pencil, highlighter, highlight those pieces of information. Now, in terms of representing a diagram, what we've got here, up the top of our diagram, this is kind of like a little tank with a bit of inflow and outflow there. Up the top here are our inflow quantities, dV dt and dx dv. Now, if you find that those aren't quite sitting well with you, what you could do is copy the units given to you in the question. So dV dt can be thought as litres per minute, and dx dv can be thought as grams per litre, depending on what kind of units we have in the question. Now, the boxes here, this is our initial information given to us, and then on the right-hand side here, the amounts of those quantities that we have at time t. And the neat way of laying it out like this is if we have mass, volume, and concentration, once we have our mass and volume, we can simply divide them to get the concentration pretty easily. And as we'll see soon, once we have our concentration, then we can simply copy and paste that into our outflow of our chemical. Okay, so first question. We have a large tank that initially holds 1,000 litres of water, in which 50 kilograms of salt is dissolved. A solution containing 4 kilograms of salt per litre flows into the tank at a rate of 5 litres per minute. The mixture is continuously stirred, and then the mixture flows out of the tank at a rate of 11 litres per minute. Now, our job here is to try and construct our differential equation, which describes this system. So as we can see, there's a lot of information here, all packed within this little paragraph. So what we like to do is take it nice and slow and try and unpack this question. So first up, what we're told is that initially we've got 1,000 litres of water and 50 kilograms of salt. So those sort of quantities there, we can put those in our initial conditions here. Next sentence, we're told that 4 kilograms of salt per litre flows into the tank. So noting the units kilograms per litre, we can think of that as dQ/dV. And so that's 4 litres, so 4 kilograms per salt, so 4 kilograms per litre flowing into the tank. That's an inflow quantity there. And we're told that it's flowing at a rate of 5 litres per minute. So litres per minute, dV/dt, is another inflow quantity. All right. Continuously stirred, not that important to us at the moment. Next sentence, we're told that it flows out of the tank at a rate of 11 litres per minute. So because it's flowing out, that's an outflow quantity. And again, the units, litres per minute, will correspond to dV/dt. So what we can do straight up is go sentence by sentence, seeing what information we have, and we can put this in our diagram. So now what we're left to do is to think about what the dQ/dV is flowing out. So in the question, we're told that Q is the amount of salt in kilograms at time t. The Q is there. Now, what's interesting is that the amount flowing in, the rate flowing in, 5 litres per minute, is different to the outflow of 11 litres per minute. So some of the difference there. So what we need to consider is how the volume changes over time. So as you just said, it's flowing in at a rate of 5 litres per minute, flowing out of 11 litres per minute. So the net rate at which this liquid is flowing in the actual tank, it's decreasing over time at a rate of 6 litres per minute. So from the actual net change of the volume of the tank at time t, we can work backwards to figure out what the volume in our tank should be at any time. So if we know dV/dt is equal to -6, what we can then do is integrate that to try and get the volume. So we can integrate dV/dt, and then we have our initial amounts, V0, which in this case is 1,000 from our question. So what we can do in any sort of situation, we can set that our volume is going to be our initial amount plus any sort of accumulation or the change in volume. So in this instance here, it's going to be 1,000 minus 6t. And so now that we know the volume at any time, we can put that in our table. All right. Now in terms of concentration, well, in our table, we've got mass, we've got volume. So the concentration is just simply mass divided by volume, which we get there pretty neatly. And so now we know the concentration inside the tank at any time. That concentration is going to be flowing out. So that's going to be our outflow of dQ/dV. And now our final job now is to determine this differential equation. So we saw before we have the net change in the amounts was the amount that's coming in minus the amount that's coming out, or the rate that's coming in minus the rate that's coming out. So by using this sort of setup here, what we can do really cleanly is to multiply our two inflow quantities. So 5 times 4 will give us 20. And then we can multiply our two outflow quantities, 11 times Q over 1,000 minus 6t. And in doing so, we see that the option corresponds to option D of our multi-choice. So to summarize, we really want to try and become comfortable with developing a strategy to unpack a worded question and to try and to, represent this in some sort of diagram, table that really works best for you. Okay. So second question now, taking up a step. In this time, we've got a tank that holds 20 litres of water, in which we've got 1 kilo of salt in there already. This time, we've got pure water is being poured into the tank at a rate of 6 litres per minute. And like before, the tank is being continuously stirred. And the liquid is flowing out of the tank at a rate of 3 litres per minute. So first up, we want to try and show that this is the differential equation of the system, where X is the number of kilograms of salt at any time. Then from there, we're going to try and solve the DE, and then we're going to then figure out how much salt has flowed out of the tank over the first 10 minutes. So when it comes to showing a DE, we want to try and try and pick apart this question to try and put it in our diagram to construct our differential equation. So just like before, right? Initially, we've got our conditions of 20 litres and 1 kilogram of salt. So that's our initial conditions there. We're told that the amount of liquid flowing in is flowing in at the rate of 6 litres per minute. There's our dV/dt. Then we're told that it's flowing out at a rate of 3 litres per minute. So dV/dt is flowing out there. Now, because it's pure water, there's no salt in there. So therefore, the xdV, that's just going to be blank. It's going to be 0. Now, we can kind of see from, like in the previous question, we have 6 litres per minute flowing in and 3 litres per minute flowing out. So the volume at any time will be the initial amount of 20 plus that change in volume. So in this instance here, our change will be 3T, because the difference, 6 minus 3 is just 3, give us 3T. And like before, that setup, mass divided by volume will give us our concentration. If that's the concentration in our tank at any time, that concentration will be flowing out. So that's going to be our outflow concentration. And then our job is to take our inflow and outflow quantities and try and get our differential equation. So on CAS, what we can do, apologies. So for the xdt, 6 times 0 is our inflow quantities minus our outflow quantities of 3 times x over 20 plus 3t to get our DE that we're trying to show there. Okay. Now, the next part of the question was to try and find x in terms of t. So this is where we're going to use our old friend DE solve. Now, if we haven't seen it in the previous webinars, that's okay. If we have, awesome. But in case not, when using the DE solve command, we need to first type in our differential equation. Because we have some sort of initial condition, we're going to put a space, type in the word and, another space, our initial condition, and then our independent variable, our dependent variable. Now, if you're using the CX2, like I will be tonight, life is pretty easy. But if you're using just normal CX1, the old black CAS, you may want to have an example of how to use DE solve in a bound reference. So if you do encounter a question like this in the assessment, you've got a reference and a guide to how to use it. Okay. So when using the DE solve, this is the structure that we're going to type in here. So we had the xdt. So the way we represent that using D in the CAS is x prime. So what we can do is to get our DE solve, we can go to menu, calculus, and then all the way at the bottom of our menu, D for DE solver. A neat little shortcut is that once we get in the calculus menu, if we press our keypad D, whoops, once we're in there, we press D, it'll take us straight to the DE solver. So if you are using the CX2, we have this neat little wizard to help us. If we're using the old CX, then we need to resort back to that syntax structure. Right? So for example, we want to type in the differential equation. So we're going to type in x prime. So to get those primes, in our punctuation button on the CAS, just underneath the enter button, we can press that to this little submenu, and there's our prime button. And we had negative 3 times x divided by 20 plus 3 times t. Okay. Our independent variable will be our time, and our amount depends on our time, so our x. Now, for the condition, we're told initially that we have 1 kilogram of salt in there. So the way we represent that is x, open bracket, 0, equal to 1. So what we're saying here is that initially the time equals 0, the x value is equal to 1. And then we can press enter to get our differential equation there. Okay. So as I said before, I do recommend we put an example in a bound reference just so we have an example to go off in a situation of an assessment. Okay, so next part, once we have our x in terms of t, next question was to find the amount of salt that has flowed out of the tank in the first 10 minutes. To calculate the outflow quantity, what we're going to do is look at the integral from 0 to 10 through the first 10 minutes. Now the outflow quantity, the amount that's actually flowing out, is given by this expression here, 3 times x over 20 plus 3t. So we're going to take that and put it in, that's not going to work. So we're going to put it inside of our integral there. So 3 times x over 20 plus 3 times t, integrate with respect to t. Now, doing this integral, we are in a bit of trouble. So because it's going to integrate with respect to t, we've got an x in there. So ideally, we would have x in terms of t. Now, what I might try to do to get around this is using a pre-prepared slide, is that we saw before, when we solved the DE, we got x in terms of t. So to work out the amount of outflow that has occurred over the first 10 minutes, we can look at our outflow quantity. Now, because there's x here, we need to sub in x in terms of t, and we got that from solving the differential equation before. So what we can do quite neatly to get that, demonstrate that, is we can type that in the integral, and to sub in our expression for x, we can put our vertical line, control equals, such that, and then because we want x equals our expression, we can press up. Once it's highlighted, we can press enter to bring it down. And then because the question asks for 1 decimal place, we can press control enter to get our decimal answer. Okay. So question 3 now. And they're just the work solutions there. Question 3. We have a water storage plant that has discovered that one of their 10,000 water tanks, so 10,000 litre water tanks, has a chlorine concentration of 4 milligrams per litre, which is above a safe limit of 2 milligrams per litre. And their way to reduce the chlorine concentration is to pump pure water into the tank at a rate of 40 litres per minute. And we're also told that the liquid inside the tank is pumped out at a rate of 80 litres per minute. Here we're saying that x is the amount of chlorine in the tank at any time. And just like before, we want to show that the differential equation that describes the system is given by negative 2x over 250 minus t. So there's a bit of a theme here, a bit of a pattern in terms of how we can go about these questions. Like before, we're going to identify our initial information. So first up, we've got our 10,000 litre tank of our volume. This time, however, we've got a concentration of 4 milligrams per litre. We can put that in our concentration section. The liquid's flowing in at a rate of 40 litres per minute, so there's our inflow dV/dt, and our dV/dt coming out is 80. And like before, to determine the volume in the tank at any time, it's going to be 10,000 plus some sort of change. And we can see from the diagram that the net flow of water will be negative 40. So 40 minus 80 to get negative 40. Therefore, our volume overall at time t will be 10,000 minus 40t. And once we've got the volume, we can divide mass by volume to get the concentration cleanly. And just like before, if that's the concentration inside the tank, it's also going to be the concentration flowing out. that'll be our dx dv. So now our job is to multiply our inflow and outflow quantities. So let's see that in action. Our inflow outflow, we had 40 minus 0 for our inflow quantities, and our outflow 80 minus that concentration to get 2x over t minus 250. Now, don't be too alarmed if this thing looks a little bit different to what we had in the question, because we had negative 2x over 250 minus t. They are an equivalent expression. It's just the CAS likes to express pronumerals with a positive coefficient if it can. So this thing is the exact same as what we have on paper. Okay. Next step, like before, we want to try and find x in terms of t. So if we try to use dsolve, right? So another way to get dsolve is from the catalog. This book button just underneath the delete button. To press that, we can press the D button on our keypad to take us to the D section, and then scrolling down, we can get our dsolve there. Okay. Now, like before, we can type in x prime. So get our prime symbol, the punctuation button just underneath enter to get x prime is equal to. So we can either use our expression from before or copy it off the question. Just make it easy, I'll copy what we have just up above, 250. Okay. Now, for our initial condition, we need to put in the space. So to type in our space, the space button is just at the bottom of our CAS on the right-hand side. And the word and, we just type that in, another space. All right, now we need to think about what the initial mass is of the tank. Now, in the question, we were given the concentration and the volume. So we actually need to work backwards to get the initial mass. So this is another benefit of laying out information like this, such that we have mass over volume over concentration. Because if we are presented with a question that is a bit left of field, where we're not given the mass straight up, we can work backwards to get it. Okay? So to get our mass, we can just simply multiply volume and concentration together. So what we can say is that initially, and in case we are a bit shaky in an exam, we can do 4 times 10,000. Right? Our independent variable is t, and x depends on t. So there is our expression for x in terms of t. Our next one, from here, we want to try and find the volume of the water in the tank when our concentration reaches 3 milligrams per litre. Okay, so we actually know from this table, we know the concentration in the tank at any time, which is this expression here. So we want this concentration to be equal to 3. We'll know when it's equal to 3. So what we can do is we can solve when our concentration, which was x over 10,000 minus 40 times t, when that thing is equal to 3. And because we don't know what time it occurs, we're solving for our t. Now, similarly to the previous question when trying to integrate, and we had an x and a t in there, because we have an x in here, it is a bit annoying. However, we do know x in terms of t. So we can substitute it in our previous work into here to get everything in terms of t. So just like before, we can do control equals to get our vertical line such that, and we can press up to highlight and enter to bring it down to get our t value. So we now know when the concentration is 3 milligrams per litre. The actual question itself was, what is the volume when the concentration reaches 3 milligrams per litre? So we're halfway there. Now the volume, we can either look at our diagram to get our volume. because in our diagram, we know the volume at any time. It's just 10,000 minus 40T. So what we can do is to say that volume is equal to 10,000 minus 40 times T. And we like to substitute in this T value. So just like before with solve, we're going to do our vertical line such that T is equal to 125 over 2. And we get a neat answer of 7,500. Okay. All right. So something happens after the concentration reaches 3 milligrams per litre. Once the concentration reaches 3 milligrams per litre, the water being pumped in the tank is now switched to a chlorine-treated water with a concentration of 1.5 milligrams per litre. And the rate of inflow is increased to 80 litres per minute. So now things have changed, and we like to now show that the differential equation describing this system is given by 120 minus 4x over 375. So we need to be now mindful of what our initial conditions are. And so our initial conditions are going to be those when our concentration in the tank is 3 milligrams per litre, because that's when this change occurs. So our concentration is 3. We know the volume, we just found it before, was 7,500. Right? The inflow, well, that's been increased to 80. Know when the question has the outflow being changed. So the outflow is still 80. We're told that the liquid coming in has a concentration of 1.5 milligrams per litre. So now we have the XDV up the top here as 1.5. And because the inflow is the same as the outflow, our volume isn't changing. So the volume at any time is still going to be 7,500. Okay. So from here, we can get our concentration quite easily with mass over volume. So X over 7,500 to get a concentration. And just like before, that concentration is in the tank, which will be the concentration flowing out of the tank. Now, we may need to solve the differential equation again. So what we can do is do a bit of hard work and work out the initial mass in our tank. So just like before, we've got the volume, we've got the concentration, so we can multiply these two guys together to get our initial mass in the tank when that change occurs. So when trying to figure out our DE now, just like before, what we can do is look at the inflow minus the outflow. So we had dx on dt. Our inflow quantities, we had 80 times 1.5 minus 80 times x over 7,500. Okay, and that is the differential equation that we wanted to show. So, final one, we want to try and find out how long it takes for the change in the chlorine-treated water pumped in to get to the safe level of 2 milligrams per litre. Okay, so ideally what we like to try and find out is when our concentration is equal to 2. Right? And we've kind of seen something like that before. Now, because we want to find a time, we like to solve for t, but the problem is we've got an x in there. So we need to first of all find out x in terms of t. So just like before, we're going to be solving a differential equation. So we can use our d solve from before. Okay. Our x prime is equal to 120 minus 4 times x over 375. We just put in our initial condition once again, so space and space. And we had our initial mass from our table was 22,500. So we can type that in. Right. Comma t, comma x. And there's our x in terms of t. So now we'd like to find out when the concentration reaches the safe level of 2 milligrams per litre. So our concentration in the tank was X over 7,500. Right? When that's equal to 2, we're finding out the time. So we need to solve for T. And as we just said, that because X is in terms of T, just like before, we need to sub in this expression for X. So control equals a vertical line such that X is equal to that thing. And then we wanted it to a couple of decimal places or to the nearest whole number. So control enter, we get 102.995. Now, what we're going to do is, it's not quite at 102, the nearest whole number, the concentration isn't quite reaching 2 just yet, but when it is 103, it will be 100, so it will be equal to or less than 2, less than that safe level. Right, and we can kind of see that. So if we had our X value, if we had X over 7,500, sorry, 7,500, right, such that our X value, and we like to sub in T equal to 102. So the way we can do that is space and T is equal to 102. We see that the concentration isn't quite below 2 yet, it's still above the safe level. But if we change that to being T equal to 103, we'll see that that concentration is now below the safe level, and therefore our answer will be when T is equal to 103. So thank you for joining us for tonight's webinar. If you have any questions, please feel free to put them in the chat. But all the best for your studies for the rest of the year. And thank you for joining us once again tonight.